Okay, the title of this lesson is Similarity, and it's Lesson 8 of Module 3. We are, in this lesson, going to put together some of the things we know about dilations and come up with a formal definition of similar. We started out this module talking about similar, meaning same shape, but not necessarily the same size. So we're going to show how to use a dilation in order to show two figures are congruent. Okay, so let's look at an example. So we've seen how dilations will either magnify or shrink a figure proportionally. So all segments would be in proportion to the other segments in the figure when the figure is dilated, and all the angles remain the same. So the angles remaining the same ensures the same shape, and the dilation ensures that it's in proportion. So not necessarily the same size as the original figure. Okay, so these two figures that are on the screen here, although they're kind of maybe not exactly, they look as though they're in proportion to one another. So we could call them, let's name them. So we have figure S1 and S2. It looks as if I could perform a dilation on figure S1 and make it the same shape and size as figure S2. But could I get it to lie exactly on top of figure S2? Well, not necessarily, because they look like it's been dilated from maybe a different center or something. So we would need to do something else. So we could do something like once we dilated figure S1 to look like figure S2, we would then need to translate it. We could translate by a vector, and let's see what that would look like. So if this point would be correlating to that point. So if we had a vector that would translate there, and then we could rotate the figure and make it map exactly on top. So that leads us to our definition that we're going to use for similarity. So you should find a place to write this in your notes and record this, because we're going to use this for the length of this lesson and the following lessons. Okay, so here's our definition. Two figures are said to be similar. So similar is what we're defining here. Two figures are said to be similar if one can be mapped onto another by a dilation followed by a congruence. And remember, a congruence is a sequence of rigid motions like translations, reflections, rotations, or a congruence followed by a dilation. So in other words, it doesn't matter what order you do the dilation and the congruence in, as long as the two figures are mapped onto one another. So in our example that we just gave, the ice cream cone looking shapes, they were in proportion, but a dilation alone wouldn't map them onto one another. So a dilation alone isn't always sufficient to show similarity, but a dilation followed by a congruence, as long as the figures are mapped onto one another, will show similarity. Okay, so we're going to look at several examples now, and you're going to pull in what you did from Module 2 along with what we've been doing on dilations in Module 3, and we're going to combine dilations and rigid motions, the other transformations we studied, to show similarity. Find example 1 in your notes. You have this diagram. I have written the vertices of these triangles larger so that we can see them. And so you could label your paper the same way. It makes it just easier to talk about. So let's read it. In the picture below, we have triangle ABC that has been dilated from center O by a scale factor of R equal to 1/2. So you can probably see that. Here's ABC. It's been dilated, and it became the triangle A prime, B prime, C prime. So that's that right there. It is noted, and the center of rotation is the origin here. It is noted by A prime, yeah, we already said that. We also have triangle A double prime, B double prime, C double prime, which is congruent to A prime, B prime, C prime. So that's what we're given. We know these two triangles are congruent, and we know that these two triangles are similar. Well, we know that they're dilations of one another, okay? And it says, describe the sequence that would map triangle A double prime, B double prime, C double prime onto ABC. So we want to map this, we want a sequence that will map this triangle here onto this triangle. Okay, so what we might want to do, since we have this dilation here, is think about if this is a scale factor of 1/2 that took ABC to A prime, B prime, C prime, what scale factor would take A prime, B prime, C prime back to ABC? Okay, so maybe from past lessons, from what we've done in the first half of this module, you would realize that a scale factor R equals 2 would map that back onto. So we would need R equals 2 would take A prime, B prime, C prime back to ABC. Okay, so, but if we dilate A double prime, B double prime, C double prime by a scale factor of 2, let's look at what would happen to that. And let's just use our coordinates to figure this out. So what are the coordinates of A double prime? The coordinates of that are, let's fill this in, B double prime coordinates and C double prime coordinates. All right, so here are the coordinates of A double prime, B double prime, C double prime. They're 11, 4, 13, 5, and 15, 3. So I'm going to dilate that triangle by a scale factor of 2, and I'm going to get the following coordinates. I'm going to get 22, 8 for A, and I'm going to call it A triple prime, okay? Then I'm going to get 26, 10 for, let's use my tool here, 26, 10 for B triple prime. Shoot, sorry. B triple prime here. And then down here is C triple prime, and its coordinates are 36. Using what we know about coordinates, and so let's go ahead and connect our vertices of this triangle. And there is the dilated triangle. Okay. So since we've been told that A prime, B prime, C prime is congruent to A double prime, B double prime, C double prime, I know that when I dilate by a scale factor of 2, that these two triangles are congruent now. A triple prime, the triple prime triangle, and the original triangle ABC. Because I was told, I know the scale factor. But this one's way over here, so it isn't mapped onto ABC yet. So we have dilated by a scale factor of 2 using what we know about the coordinates, right? We just had to double the coordinates to get this dilation here. And you can see they look congruent here. So now I just need to figure out how can I define a congruence that will map the triple prime triangle onto ABC, and then I'm done. And so hopefully you see that a translation alone will do that in this case. And so let's go ahead, we can map any of the coordinates we want onto the corresponding coordinate. We're going to do it a little differently. In the past, we would have said, get a vector, and we'll draw that vector. So say we wanted to to map B triple prime onto B, we would have used a vector B triple prime B. I got it on there. Let me get it right. Well, close enough. We would have used that vector there, B triple prime to B, to describe that congruence. But what we're going to do now that these are all going to be on the coordinate plane is there's another way you can define a translation, and that is to show, I'll pick a different color for this, to show how many spaces you're going to move horizontally and vertically. So to get B triple prime over to B, I'm going to go, this ends up being 20 units if you count it on your graph, 20 units, and what way did they go? So 20 units to the left and 2 units down. So let's summarize what our sequence is here. So we were told right down here, describe the sequence that would map triangle A double prime, C double, B double prime, C double prime onto ABC. So that sequence is dilate from center O, the origin, dilate from the origin by a scale factor of R equals 2, of R equals 2, then, so there's our dilation, followed by congruence. Then translate (20 units left) and, let's get me some room here, 20 units to the left and 2 units down. Two units down. Now, since we haven't been defining translations that way, we should probably verify that no matter which point I pick, A, B, or C, it would work. And so we could start from A here, if we went, or A double prime, if we went 20 units to the left and 2 units down, we would come to point A. And from C triple prime, 20 units to the left and 2 units down takes us to C. And our original count was right here. Okay, so that's another way you can define a translation. You can define it by a vector if you're just out in space. But if you're on the coordinate plane, you can define it directly by how many units in a horizontal direction, left or right, and how many units in a vertical direction, up and down. Okay, and so because we could describe a sequence that would map A double prime, B double prime, C double prime onto triangle ABC, we can make this statement. We can say that triangle A double prime, B double prime, C double prime is similar to triangle A, B, C. Okay, here's another example. You do not have this one in your notes, so you can just watch. You can just watch this one. So let's read it. In the picture below, we have triangle DEF that has been dilated from center O, the origin, by a scale factor R equals 3. So it's noted by D prime, E prime, F prime. So hopefully you can see this, this dilation of this triangle to this one, especially if you look from the origin through these points. Remember those rays that dilate those points. So this is a dilation here. And what else do we have? We also have triangle D double prime, E double prime, F double prime down here, which is congruent to triangle D prime, E prime, F prime. Okay, so these two are congruent. You can see that because of this, they look the same size, don't they? And we're told they're congruent. And so here's what we want to do. Similar to our last example, is we want to map this D double prime, E double prime, F double prime onto DEF. So I'm going to see if we can map this directly to here. And so remember what we did in our last example. We figured out what scale factor would map, would make them the same size. And then we used a translation to map them directly onto one another. Okay, so this problem's a little different. One thing that's different is the scale factor is r equals 3. So this triangle has been magnified. Another thing is we might not be able to just use a translation. A translation alone is not going to map these. You're kind of seeing that, I don't know if you can see a reflection just yet, but there's a reflection going on here. So let's, so we want to define a sequence because we want to show similarity. So we're going to define this sequence. So we're going to need a scale factor, not of r equals 3, but it's reciprocal, right? So we're going to dilate. Let's start writing this sequence. We're going to dilate from the origin with r equal to 1/3. And so let's do that. And if we can dilate this triangle with scale factor r equal 1/3, and so it's going to look, I'll show you a picture of what that looks like. Since you're not drawing this one, I'm just going to do this for you. All right, so when we do, when we use r equal to 1/3 on the coordinates of D double prime, E double prime, F double prime, we end up with this triangle right here. Now, the origin was part of the triangle, so notice that the center of dilation never moves, so it stayed in the same place, and we got this other dilated triangle, which is really just part of the larger triangle here. Okay, but hopefully you can see they're similar. Notice that these two lines here are parallel, D double prime, E double prime, and then D triple prime, E triple prime. Okay, so we have those triangles. So now we want to, we've done our dilation, and now we want to follow that by a congruence. So what I'm going to do is map the F triple prime to point F. And I'm going to do that by a translation. So let's think about how far do we have to translate it. Okay, so we're just going to, let me get it colored so you can see the difference here. Our translation is going to go 2 units to the right. So we're going to, I'll keep with this, translate 2 units to the right. Okay, and so everything's going to go 2 units to the right. So let's move these points here, and my D point is going to move 2 units to the right. So my new image is right here. All right, so now I've got an image right there, and so the last rigid motion I'm going to do is going to be to reflect it over the x-axis. So I'm going to reflect that translation, reflect over the x-axis. Okay, so on the reflection, and then they're mapped onto one another. So what I've done here is I've shown that D double prime, because I was asked to map. This is what I was asked to do. So now we know that D double prime, E double prime, F double prime is similar to D, E, F. Okay, so this symbol is similar to, might be new to you, and it's different from the congruent sign. Congruent is the equal sign with the bar over it to show two figures are congruent. We saw that, and then we use just the little squiggle to show the similarity. Okay. Okay, here's another example. We are told in this that triangle ABC is similar to triangle A prime, B prime, C prime. So, and we're just asked to find a sequence of a dilation followed by a congruence that would prove that these two figures are similar. So again, you don't have this in your notes, so just watch. Looking at the two triangles, I'm going to try to map ABC onto A prime, B prime, C prime. So what dilation would I need to perform to do that? And if you're looking here, if you look at the length of these segments here, and the corresponding segment over here, so we're going from 6 down to 3. This side of the triangle is 2 down to 1. So you can see that the scale factor would be 1/2 if I'm going to go down here, because, and I can, if I wasn't able to just see that, maybe the numbers didn't come up as nice. Remember that the scale factor is always the dilated length, and we talked about this in previous lesson, dilated length over the original length. And that will always work for us. So our scale factor in this would be the dilated length I want to get to would be the A prime, like for that segment would be A prime, B prime, and the original length would be A, B. So that would be 1/2. Okay, so if you don't remember this for sure, that would be a good thing to write in your notes. The scale factor is the dilated length over the original length. And so in the case of this diagram, I've got my dilated lengths are the ones down here, and my original lengths are up here. Okay, so let's get rid of all this extra stuff here. So I want to dilate this. So remember, we're working on the coordinate plane now. So if I want to dilate point B here, for instance, and its coordinates are -2, +2, the dilated B would be right here at -1, +1, if I just took for R equal 1/2. So I'm going to do a dilation. Let's write down our sequence here, since that's what we need to find. A dilation with R equal 1/2 from center O, the origin. Okay, so C, the coordinates look like -8 and 2. So I'm going to go to -4, 1, taking half of each coordinate. And point A is -2, 4. So that's going to be half of -2 is -1. Half of 4 is 2. So my triangle is going to end up right here. Okay, so I can see with scale factor 2, a dilation with scale factor 1/2 from center O, I now have a new triangle, and I can name it. I could name this a double prime. This would be B double prime and C double prime. Now I need to get define my congruence that's going to take this double prime triangle onto exactly onto this one down here. So let's look at what that would be. And again, you can either draw this or you're just watching. I need to translate. So I want to get, for instance, B double prime directly onto B. So can you see what that translation would be? And remember, we're defining our translations by how many units up or down and how many units horizontal units. So I'm going to translate, this is my next motion here, next transformation, translate this A double prime, and I'm going to translate 3 units right and 4 units down. Or I could say 4 units down, 3 units right. It doesn't matter what order I do them in. It's going to get me to the same place. And notice every point we move will go, it doesn't matter which one we pick, they will all, they'll all follow that rule. Let's get rid of this here. So let's show it with A. If I go 3 units right, 4 units down, there's my point I want to do. And with C, I'm going to go, so let's draw this triangle. Let's see, I've mapped B prime, so I'm going here to here. B prime goes 3 units and 4 units. So there's A and B. Now what happens to C when I go, I'll do it with a pointer here. C is not going to end up over here, is it? It's not going to be on it yet. So C is going to go 3 units to the right and 4 units down. It's going to end up right there. So let's put point C there. C is going to end up here. No, it's not. It's going to end up here because I'm going 3 units and 4 units. Okay, so here's my new triangle right here. After the translation, I'm right there. So hopefully you can see now all that's left to do is to reflect. And with the reflection, I need to give my line of reflection. So I'm going to reflect over segment A prime, B prime. So I'm going to reflect over this segment right here, and these two triangles will coincide exactly. So I've defined a sequence right here of a dilation, followed by a translation, followed by a reflection that shows that triangle ABC is similar to A prime, B prime, C prime. Okay, here's another example for you to watch. In the diagram below, we have 2 similar figures. Using the notation, we have that triangle ABC is similar to triangle DEF. We want to describe a sequence of a dilation followed by a congruence that would prove these figures to be similar. So we're trying to map triangle ABC onto triangle DEF. So one thing I want to point out about these similarity statements is that the order matters. If I say that triangle ABC is similar to DEF, what I'm saying is that vertex A corresponds to vertex D, B corresponds to E, and C corresponds to F. Okay, so I've got this segment AC here, and I'm told it is 18 units. If you can't see that, 18 units long. And I know from my similarity statement that A and C are going to correspond to D and F. So DF over here is 6 units. So this one is 6 DF. Okay, so I can figure out my scale factor that I would need for my dilation. So I want to first make these the same size, and then I can define some rigid motions that would map them onto one another. So my scale factor R, again, is going to be the dilated length, which is going to be 6, over the original length, which is 18. So if I reduce that or simplify that, I see that my scale factor is 1/3. So my first thing I'm going to do, since I'm told to describe a sequence of a dilation followed by a congruence, is I'm going to dilate this triangle ABC with a scale factor of 1/3 from the origin. And so I can see this is point B. Right here is at coordinates 3, -3, 6. So -1, 2 would be the location of my dilated point B. And let me plot the others for you quickly. Okay, so taking those with a scale factor of 1/3, I have dilated this triangle, and I'm going to call it A prime, B prime, C prime. And so it sits right there on the coordinate plane. And so now I can see, looking at these, I can tell that these A prime, B prime, C prime is congruent to DEF, but not mapped onto it. So I'm going to define a sequence of rigid motions that will do that. Okay, so I'm going to, now I know that point vertex B corresponds to vertex E because it's in the same position on my similarity statement. So I'm going to translate down 2 and to the right 7 to map B to E. And so then I would have, so if I take all the points of this triangle, I'm going to take C down 2 and over 7. It will be right here. And then A goes down 2 and over 7, and it ends up here. So now my triangle sits right there after the translation. So I could just reflect it on this line here, but where's my pen? I could reflect it across this line, probably. But what I'm going to do, I want to be able to define the line in terms of the figure. And so I can do a rotation. So if I rotate this, rotate D degrees around point E this way, I can map segment BC here onto, let's see, pointer here. I want to rotate this way so that this segment here lines up with EF. So I've got B prime, C prime here mapping to EF, and then I can translate across EF, and then it's mapped on. So this would be, and I would, if I were doing this, we're moving through these examples, trying to move through quickly. So we have the dilation, and I'm abbreviating. So I have a dilation with R equals 1/3. Then I had a translate, and that was 7 to the right, 2 down. Then I rotated wow, this one I'm kind of getting everything in there. Rotated around point E, around point E, d degrees until EF and B prime C prime match, and then I reflect over EF, segment EF. Okay, so we had a dilation, a translation, a rotation, and a reflection. Cool, so we had a dilation followed by a congruence, and we proved that those two figures were similar. Okay, so this next example says, knowing that a sequence of a dilation followed by a congruence to find similarity also helps determine if two figures are in fact similar. So here's the same diagram that we had a minute ago with slightly different dimensions. What if we were told that BC was 15 units, AC was 18, and then down here I had EF at 4 and DF at 6. So if we had something like that going on, if I compare BC and EF, I would have this. BC to EF is 15 over 4, and AC to DF would be 18 over 6. So this one would equal 3, but 15 over 4 is not equal to 3. Therefore, I know that ABC is not similar. That's not really how we write that. Is not similar to DEF. Triangle DEF and triangle ABC. So they're not similar because there would not be a dilation that would map, that could make triangle ABC the same size as DEF. I could not do that. Therefore, I couldn't define a dilation followed by a congruence. Okay. Okay, one last point before we move on to the exercises for you to do. We have these two figures, figure A and A prime, and notice that there is some proportion going on, like some sides are in proportion 16, whoops, wrong pen there. 16 and 8 are in the same proportion as 24 and 12. They're both double. 16 is double 8, 24 is double 12. But could I say that figure A is similar to figure A prime? Well, it might seem really obvious to you, but maybe not to everybody, that I could never map a 4-sided figure onto a 3-sided. They're different shapes. So even though there is some proportionality in some of the sides going on, I could never define a sequence that would map these, so they are not similar figures. Okay. All right, so we're going to move on to the exercises that you have in your packet now. So let's look at exercise 1. All right, so we have example 1 here, and this is for you to do on your own. So I'd like you to go ahead and pause the video and try to use the methods that I've been showing you in the examples to do this. But let's read it together. Triangle ABC was dilated from center O, the origin, by scale factor r equal to 1/2. The dilated triangle is noted by A prime, B prime, C prime. So then another triangle another triangle, A double prime, B double prime, C double prime, which is right here, is congruent to A prime, B prime, C prime. Okay, so we have this congruence statement. We're supposed to describe a dilation followed by a basic rigid motion that would map the double prime triangle onto triangle ABC. So we know this congruence here. We know the scale factor between these two. So this will be a dilation followed by just one rigid motion that would map those. So go ahead and pause and do that and come back and we'll correct. We'll look at a solution for this. Okay, so I have dilated our triangle A double prime, B double prime, C double prime. I know that my dilation needs to have a scale factor of 2. So I've dilated this triangle to another triangle that I'm going to call A triple prime, B triple prime, C triple prime. So I've written that down here. So this triangle is dilated with scale factor of R equal 2 from center O, the origin, giving triangle A triple prime, B triple prime, C triple prime. So now all we need a basic rigid motion that will move the triple prime triangle over to our ABC triangle. So that's going to be a translation, and that's going to look like this. So notice that to map B triple prime onto B, I need to go up 4 units and 12 units to the left. And the same thing is true for point A triple prime to A, and the same thing is true for C triple prime to C. Up 4 and over 12 will do that. And so we would define that by describing that translation. Okay, so all I need to say is, after the dilation, is then translate triangle A triple prime, B triple prime, C triple prime, 4 units up and 12 units to the left. And that will map, the dilation followed by the translation will map A, whatever we were asked to do here, A double prime, B double prime, C double prime onto ABC. Right there. Okay, now look at exercise 2. Try it on your own and then pause the video and come back and we'll work through it together and see how you did. Okay, so this one is asking us to describe a sequence. Remember, it's going to be a dilation followed by a congruence that would show triangle ABC similar to A prime, B prime, C prime. So the first thing we're going to want to do is to think about our dilation. We're going to do it from the origin, but we need to know what our scale factor is. So we're going to have a dilation about the origin. Or we could say about center O. Let's do that. About center O with scale factor R equals what? Okay, so my scale factor is going to be my dilated length. R is going to equal my dilated length. So let's look at one of the segments in our triangle. So I would pick AB. And so its dilated length is going to correspond to A prime, B prime. And that's because of our similarity statement here. Point A and A prime are in the same location in my similarity statement. B and B prime and C prime. Okay, so we want to look at A prime, B prime over AB, length AB, and length A prime, B prime. And so A prime, B prime is 1, 2, 3, 4, 5, 6. And AB, the length of AB is 2. So that gives me a scale factor of 3. So R equals 3. So I'm going to do a dilation around center O with scale factor R equals 3. Okay, and so what's that going to look like? Well, I'll draw it for you if you haven't done it yet. Okay, so I've drawn the triangle, the dilated triangle, dilated about the origin with scale factor R equal 3. Okay, hopefully you're doing this before you watch me do it. Once again, it's not helpful for you just to continue watching me do these examples. All right, what was your next? What was your next? Now we have the dilation. Now we're going to have the rigid motions that will map our dilated triangle here onto A prime, B prime, C prime to complete that similarity. All right, so let's look. When we had these in Module 2, a really good strategy would be to get one, to use a translation to get one of the vertices matched up. And so the one I'm seeing here is to map, and this is not the only way you could do it, but to use this translation to map this, we could have labeled this with double primes like this, but you don't need to. But to define this, so if I take this triangle and translate it, I'm going to do this so I can translate 10 units to the right, and I have to look at how far I go down, 1, 2, 3, 4, and 5 units down. Okay, and remember before we would have said along a vector, but now when we're on the coordinate plane, we can be really specific about how many units over, which way horizontally and vertically. Okay, so that's our translation. So we have a dilation, a translation, but we're still not quite there yet because, see, our triangle is going to be right here. And let's see, it's going to be, how many is this? Yeah, and then coming over, sort of like so. So our triangle's there. So now we need a rotation. And instead of saying d degrees on this one, we can actually say how many degrees it is. So what is the degree of this rotation right here? Around point C, and it is a counterclockwise rotation, which would be a positive number of degrees. So it's around point C, 90 degrees. And that will map triangle, this whole sequence will map triangle ABC onto A prime, B prime, C prime, and it shows that they are similar. So that's my sequence there. Okay, that's exercise 2. Now, why don't you tackle exercise 3, pause the video, and come back and check your work. Okay, so if we are going to show these two triangles similar, it says, are they similar? If so, describe a sequence that would prove ABC is similar to A prime, B prime, C prime. If not, state how you know they are not similar. Okay, so if they are similar, we can find a dilation that will make these two triangles the same size. Once we've done that, we can move one on to the other. So we need to find our scale factor. Okay, so if they are similar, we'll have a scale factor. Now again, ABC, A prime, B prime, C prime. So we can look at segments such as AB, AC, BC, all of these, and compare them. Okay, so again, our scale factor is our dilated length compared to the original. Okay, so it's telling me how many times bigger is the dilated length than the original, or smaller, as the case may be. So if we look at, let's first look at segment AB. So A prime, B prime would be the dilated, and AB would be the original length. So AB is 18, or no. AB is 15, and A prime, B prime is 10. Okay, so you gotta make sure, because these triangles are sometimes rotated or reflected, so you have to go by the labeling. Okay, so it's those two segments here, and if I simplify that, I get 2/3, or 2 to 3. So because we've been given all these lengths, we need to check all of them for the scale factor. So let's look at B prime C prime over BC. That would be BC is 6, B prime C prime is 4. Okay, that also simplifies to 2/3. Okay, then let's look at A prime C prime over AC, and we get A prime C prime is 12, and AC is 18. You can see we can take out a common factor of 6 and get 2/3 for that as well. So it does look like we have a dilation here with a scale factor of 2/3. Okay. Okay, so I cleaned it up here. Our scale factor is 2/3. So we're going to dilate triangle ABC with a scale factor of 2/3. So we're not on the coordinate plane now. So we get to choose our center, and I am going to, we can choose even A as our center here. So we're going to dilate triangle ABC from center, from center A by scale factor R equal to 2/3. All right, and when we do that, we will end up with a triangle here, and it will be this triangle right here. So we will have taken everything, 2/3 of it, so length A prime C prime right here is 12, and then 10 and 4. So now we have these two triangles that are the same size, but they're in different locations. So because we're not on the coordinate plane, we're going to go ahead and map point A to A prime. This would probably be the simplest, but not the only way you could do this. Remember, you may have done it a different way. But when we're doing these congruence transformations, it's really handy to get one corresponding vertex or vertex mapped. So I'm going to map A to A prime. So I'm going to translate along vector A prime, and then I would have those points. So first dilate, then translate along vector A prime, and then it looks like a rotation. I'm going to rotate around point A, or A and A prime are the same point now. So I'm going to rotate d degrees until the triangle maps to triangle A prime, B prime, C prime. Okay, so if I just rotate this around, then this point here is going to map to this point, and this point will map to that one. And A will already be mapped. Okay. How you doing? Staying with me? We are almost there. So we're going to do exercise 4, and then we'll summarize and we'll be done. Okay, in exercise 4, again, try this on your own and then check your work against mine. So they're asking, are the two triangles below similar? If so, describe a sequence that would prove ABC similar to A prime, B prime, C prime. If not, state how you know they are not similar. All right, so like in the last exercise, you're going to want to check that everything is proportional. All the corresponding side lengths need to be proportional in order for us to be able to do a dilation and then to find a congruent triangle. Okay, so go ahead and pause, check those, and come back and check your work. Okay, so this shows the work of comparing all the corresponding side lengths. They all appear to be equal to 4/3. This one, 10.67 and 8 divided by 8, is the only one that isn't exactly 4/3, but it's very close. They're all 1.333. So, so our scale factor is R equal to 4/3. Okay, so we're going to take triangle ABC, and we are going to dilate it with a scale factor of 4/3. And since we're on the coordinate plane, we're going to use the origin as our center. So we're going to dilate triangle ABC by scale factor R equal 4/3 around or from or yeah, it's fine, around center O. Okay, the origin. Okay, so that is our dilation. Now we need a congruence. And in this case, we've said we want to use the coordinate plane to do this. But in this case, notice that A, B, and C, we don't have a good, we don't know what those points are because they're not on grid lines. So we're going to just use a vector when we're done. So we're going to dilate this, this triangle by a scale factor of 4/3. And that's going to give us a triangle that is congruent to A prime, B prime, C prime, but not in the same location. So what I want to do is map up a point. So I'm going to translate along, and I'm going to choose C. I'm going to translate along vector C, C prime. And that's going to give me a triangle right here, kind of like that. Not exactly like that, but you get the point. So I'm going to translate along C, C prime, and then notice what I'm going to have to do next. I'm going to have to rotate around point C. until ABC maps to A prime, B prime, C prime. And you might notice that that's a 180-degree rotation, but let's just put D degrees. That would be fine. Okay, so that is the last exercise for you to do. So just kind of to summarize what we've learned, we could go back to the definition of similarity that we've been using. Okay, so that would be this that you wrote down at the beginning of this lesson. That two figures are said to be similar if one can be mapped onto another by a dilation followed by a congruence, in other words, a sequence of rigid motions, or a congruence followed by a dilation. All of our examples, we did the dilation first, and then we did the congruence. But you could do it the other way around. So either way, you could do that. And so once we knew that, then we could say that a triangle, or whatever figure, we'll use triangle as an example. We could say, for instance, that a triangle A, B, C would be similar to another triangle, say D, E, F. And we use that, this notation right here to mean similar. All right, so we did a lot of examples like that, and you have several to do in your problem set. So just take your time and describe the dilation and the translation with all the details that are needed to for each of those transformations. Okay, so read your questions carefully and look through those. Some of them might seem rather obvious. Some of them might be a little trickier. We are taking 2 days for this lesson, so because there is quite a lot to do, and this was quite a long video. So we will have 2 days for this lesson, and then we'll move on to lesson 9. Okay, good luck.